welcome back to Science Fantastic with Professor Michio Kaku. Today we're going to talk about one of the greatest chases of all time in physics, the search for the theory of everything. An equation perhaps no more than 1 inch long that will allow us to, quote, read the mind of God. And with us today is Dr. Graham Farmiloe, author of a new book talking about this quest. The book is called The Universe Speaks in Numbers: How Modern Math Reveals Nature's Deepest Secrets. And I should also point out that there's a controversy about this whole theory. Some people say, bah, humbug, it's all a wild goose chase. Where is the beef? I mean, where is the experimental proof that we are getting closer and closer to a theory of all creation, an equation that will summarize everything we know about science for the past 2,000 years? Well, we're going to ask Dr. Graham Farmiloe that question. How do we really know that we're getting close to a theory of everything, or is it really just an optical illusion? I should also point out, in all fairness, that I have a stake in this debate. I work in string theory, and it's now the subject of a controversy. Several physicists have now come out and said it's all an illusion, a wild goose chase. We've been hypnotized by the beauty of string theory, and it's just gibberish. It's just mathematics. I mean, where's the beef? So once again, with us today is Dr. Graham Farmiloe, and the book is called The Universe Speaks in Numbers. So, Graham, let me ask you a question. How did you, as a youth now, as a child, first get interested in science and eventually physics?
Well, I got interested in physics when I was, I guess, about 10 or 11 years old. And separately, I was interested in math. And I remember very clearly being very, very surprised that you could talk about some physics in the language of math. It was not at all obvious to me that the stuff that we were learning in our math classes could be directly imported in order to study nature. And I remember now, I still remember just being amazed that, for example, when you could talk about the motion of a football or a soccer ball, a tennis ball, or what have you, and you could not just describe it as a beautiful shape of a parabola or whatever you want, or whatever shape it takes, but you could actually demonstrate that it would be that shape mathematically using some very simple principles and basic math. And I was absolutely amazed by that, and I became increasingly amazed as I realized that huge parts of physics could be summarized so beautifully in terms of mathematics.
Okay, and then why did you write your book, The Universe Speaks in Numbers: How Modern Math Reveals Nature's Deepest Secrets? Why did you write the book?
Well, there's two reasons, really. When I was training as doing my PhD in physics, this was in the 1970s. That was a time physics was almost like a party in terms of the physics of the particles inside the atom. This was a fantastic time because we were discovering the basic laws that apply to the forces within the atom. And it was in the 1970s that we really did wrap up what are known as gauge theories of the forces within the atom. Now, at that time, I remember seeing papers coming across my desk that were very, very mathematical, that didn't concentrate on explaining the data, which those gauge theories did so beautifully, but that seemed to me mathematically very, very advanced, and I hoped it would go away. And because I didn't regard myself as the greatest mathematician, but I thought that nature just couldn't be this complicated. But over the years, over the last 25, 30, 40 years, math has increasingly come to the fore as it's become more and more difficult to come up with experimental results that can really inform our theoretical thinking. And I wanted to investigate how relevant that how much faith we could put in this mathematical thinking. And here I'm speaking from the Institute for Advanced Study in Princeton. Some of the finest work has been done on this field, and I have become convinced that math is an excellent way forward at a time when we aren't blessed with quite so much experimental data on which to base our theories.
Okay, and your previous book was called The Strangest Man, a biography of one of the greatest physicists of modern times, Paul Dirac, the man who discovered the relativistic electron theory. And Dirac was famous for saying that pure mathematics and beauty and beauty are sure guides to our understanding the nature of the universe. Other people say, that's ridiculous. I mean, pure math can lead you astray. So aren't you then right now in the middle of this controversy as to whether or not pure mathematics is a guide or a wild goose chase to a theory of everything?
Yeah, that is quite right. There is a controversy, although I have to say it's not a controversy across the whole of modern physics. That there are a small number of articulate people who are disgruntled about this, but the overwhelming majority of people at the frontiers of physics, not just here in Princeton, but in Cambridge, in Harvard, in Stanford, and what have you, are completely convinced that this is the right way forward. And the person who first saw that most clearly, as you say, was Paul Dirac. Now, he was an English physicist, one of the co-founders of quantum mechanics, which was the most revolutionary theory of the 20th century. And he believed that there was an incredibly close relationship between math and our basic understanding of the rules of nature. And what he believed was that our successive best theories of nature progress. As they progress, they acquire more and more mathematical beauty.
Welcome back to Science Fantastic with Professor Michio Kaku. Our special guest today is Dr. Graham Farmiloe. So, Graham, where we last left off, we were alluding to Isaac Newton. Let's go back in time and explain how Newton revolutionized our understanding of nature by showing that nature obeys mathematics. Would you elaborate?
Well, in 1687, he published a book, the Principia Mathematica, which essentially, the title of that in modern English is The Mathematical Principles of Natural Philosophy. And even the title of that book would have astounded people at the time, because he was working in the field of natural philosophy, the subject we now call experiment-based science, and he was asserting in the very title of that book that there were mathematical principles underlying it. Now, that was not at all obvious to most people in that field, but in that great book, one of the greatest written in the history of science, he, as Einstein later said, he set out the first comprehensive, workable system of theoretical physics, a complete triumph, where he looked at, he gave the laws of motion. He described how gravity was a universal force. It applied not just to apples falling off a tree down to the ground, but to planets circling the sun and what have you, and that you could apply that mechanics, those laws of nature, to the motion of these to these cosmic bodies, and demonstrate an understanding of the path that they take. And it was extremely successful. And although people questioned about the fact that he didn't give an explanation for gravity, which is what they expected, they saw there was a lot in this. And indeed, that Newton is quite rightly regarded now as the progenitor, as the beginner of our modern understanding of theoretical physics. But in what has succeeded him have been mathematically more beautiful laws that we now have to describe gravity through Einstein's theory of gravity, and indeed new laws of motion which were set out in the 1920s that describe the matter on an atomic scale. That's called quantum mechanics.
Now, when we learn math and physics in college, mathematics, we learn about calculus. And then some people are amazed that we can use calculus to understand the motion of falling bodies.
Yep.
But isn't it the reverse? Didn't Newton discover the laws of falling bodies first, and then created calculus in order to calculate
the opposite is true. He did not. He discovered calculus decades before, when he in the mid 1660s, and in his great book in the Principia Mathematica, he used methods of geometry to do his calculations, and only later, when he published his fantastic discovery of calculus, which is about the rates of change of physical quantities, that's the way that his successors, particularly in France, people like Pierre Simon Laplace and his colleagues, that's when they brought calculus to bear on physics. Newton, I want to stress again, he did not include that in the Principia, probably because he thought that most people at the time were more familiar with geometry. But it was the French school in particular, in the late 1700s, early 1800s, that brought calculus to bear, that branch of mathematics, and really brought Newton's program to a fruition, to a conclusion. And that is why I think it is quite accurate to say that the modern appreciation of physics, the modern subject of physics, was really born in France in the early 1800s. That's when the modern category, many of the modern categories of physics were set out, and we really started to take it for granted that everything we observe should be linked up through mathematical laws, which is, of course, the modern view.
Okay, and moving on from Newton, we now encounter James Clerk Maxwell, who unraveled the next great force of nature, which is electricity and magnetism.
Yeah.
So explain to us a little bit about Maxwell's equations, which every engineer and every physicist has to memorize if they want to get their PhD and become a professional.
Yeah, that's exactly right. Well, the great American theorist Richard Feynman said that Maxwell's discovery of his theory of electricity and magnetism was the most important event in the 19th century. He said it was even more important than the American Civil War. Well, anyway, I don't want to necessarily go that far because I don't think they're directly comparable, but certainly our understanding of electricity and magnetism, we more than anybody else, we owe it to that great Scotsman, James Clerk Maxwell. He was to electricity and magnetism what Newton was to gravity. And he had a much, much harder task, even than Newton, because what Maxwell had was thousands of experimental results from all over Europe, also from the centre of London, from the laboratory of Michael Faraday at the Royal Institution. But what they didn't have was a comprehensive theory that pulled together all those different phenomena into a mathematical encapsulation, if you like. And it was in the around the time of the American Civil War, actually, that Maxwell delivered what for him was a theory about the relationship between electricity and magnetism and the ether. All three things. He believed in all three of those things, and they were connected. And he set out a comprehensive theory that explained pretty well all the data that experimenters had found. And that theory, as I say in my book, The Universe Speaks in Numbers, has been fantastically fruitful, not just of its in terms of what it seeks to achieve in its own way, but also in stimulating much of modern theoretical physics. So it was an absolutely fantastic achievement, and it was so sad that Maxwell died when he was 48 of stomach cancer, not even knowing whether his theory was the correct one. That was only confirmed a decade or so later in Germany.
But wasn't it amazing that using pure mathematics, he could show that his theory gave us wave-like solutions which traveled at the speed of light? from first principles. This is amazing, right?
It was. And everyone who has the privilege of studying physics at college, as you say, it's completely. I mean, I remember when I saw that proved to me, the equations, the modern equations that encapsulate Maxwell's theory, which incidentally he never actually wrote down. It was the modern version of Maxwell's equations was first written down in 1892 by Oliver Heaviside. That was after Maxwell died. Those are the things that we now have emblazoned across T-shirts and what have you. But you can show using those four equations that by a simple mathematical manipulation, takes just a few minutes, that you can prove the existence of electromagnetic waves which can be identified as light. Light, it basically consists of electromagnetic waves, and Maxwell was the first person to see that, and that was, as you rightly say, one of the greatest insights in the history of science.
And wasn't there also a missed opportunity because Maxwell died so young, given the fact that hidden within his theory is Einstein's theory of special relativity? Isn't that amazing that a theory written at the time of the American Civil War contains relativity if you extract it?
That is right, and you know that the person who I think it's reasonable to say saw more clearly than anybody else at the time the importance of Maxwell's equations was a person born in the year that Maxwell died, and that was Albert Einstein. Einstein was a young student, very headstrong, very bright guy, not particularly concerned to be guided by his teachers, but he, it is not just in his lectures, but much more in his own time, he studied Maxwell's equations, and we can see the evidence of that in the great work.
Welcome back to Science Fantastic with Professor Michio Kaku. With us today on the line is Dr. Graham Farmiloe, author of a new book, The Universe Speaks in Numbers, How Modern Math Reveals Nature's Deepest Secrets. And where we last left off, we were talking about the fact that during the American Civil War in England, a Scottish physicist by the name of James Clerk Maxwell wrote down a series of equations which described light. But there was a missed opportunity because hidden within Maxwell's equations is the germ of Einstein's theory of relativity. So can you explain that?
Yeah. Well, the first thing to say is that out of those Maxwell's equations, that describe electricity and magnetism, you can show that you get these electromagnetic waves, which consist of light, and out of those equations comes the speed of those waves, which is a fixed number. And that looks a bit odd. Why doesn't that depend on the motion of the person observing the waves? It looks very odd. The person who saw that Maxwell's equations have a mathematical symmetry that is extremely illuminating, the person that saw that most clearly was Albert Einstein, and he wrote a paper on what we now call the special theory of relativity that showed that Newton's idea that that space and time were universal concepts that applied across the entire cosmos, not right. But that observers traveling uniformly with respect to each other have space and their own space and time that is related to another other observer according to their relative velocity. So space and time are not fixed things, they actually depend on state of motion. And that was the basis of the special relativity that a few months later Einstein demonstrated, that gave the equation E equals mc squared, relating energy, mass, and the speed of light, which we denote by C. So yes, you're absolutely right, Michio, that came out of Maxwell's equations.
And of course, Einstein was not happy with just talking about the relativistic theory of light.
Yep.
He wanted to go one step farther,
yep,
to create a relativistic theory of gravity itself,
yep,
that would then give us an even deeper deeper understanding of the nature of gravity.
Yep.
So explain to us how that transition took place.
Well, this was perhaps Einstein's greatest piece of work, because as you say, he wanted to talk not just about objects that were moving uniformly in a straight line, but things that move accelerate under the motion of gravity, like an apple accelerating towards the Earth. And he thought he could do that with really quite simple math, but that turned out to be completely impossible. He set out his first version of what we now call his theory of gravity, the general theory of relativity, in 1912, but he could only do that by introducing the notion of curved space-time, which required the use of math that had only been discovered some few decades before, and that was an absolutely crucial part of Einstein's education, because it was that convinced him that he needed advanced math in order to do advanced physics. And that really did change the whole tenor of Einstein's attitude to physics. And particularly, it was math, in his judgment, that delivered him to the final equations in late November 1915, where in front of about 200 people in the Prussian Academy in Berlin, he wrote down a law of nature, a successor to Newton's law of gravity, which was Einstein's equations of gravity. And that, most physicists would agree, is if not the greatest achievement in 20th century physics, it was right up there. And Einstein regarded math as the thing that had delivered him to that great prize in 1915.
Okay, well, let's take another short commercial break, and after the break we're going to even go beyond Einstein to talk about, well, the theory of almost everything. We almost have it. People call it the Standard Model. But we'll talk about a controversy, because even Einstein couldn't get his head around the quantum theory. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is Dr. Graham Farmiloe, author of a new book, The Universe Speaks in Numbers, How Modern Math Reveals Nature's Deepest Secrets. Well, we started off by showing that Isaac Newton was the one who showed that mathematics can describe the nature of planets and comets and the nature of the solar system itself. And then it was James Clerk Maxwell who applied mathematics to light and showed that light is an electromagnetic wave. And then we have Einstein, who extracted relativity from Maxwell's equations that went farther and created a theory of gravity based on curved space. And now we have the quantum theory, perhaps the craziest, most bizarre theory of all, and even Einstein couldn't get his head around the quantum theory. But hey, well, I guess Einstein was wrong. So tell us a little bit about the birth of the quantum theory, and now we have something called the theory of almost everything.
Well, that's a big jump, but you're absolutely right. Quantum mechanics, which is the theory of motion and matter at the quantum level, right? Newton's laws just don't work there. This was a big surprise to scientists in the early 20th century. But we know that the world behaved differently there, and that we need different laws. Energy, for example, is quantized. It comes in discrete lumps. Now, it was in the 1920s that the most revolutionary theory of the 20th century was set out by Paul Dirac, Heisenberg, and Schrödinger, and others, mainly European physicists, and they set out a completely new set of laws in mathematical terms that, in part at least, were really very strange to physicists. But that worked extremely well in predicting, when combined with relativity, it actually predicted the whole notion of antimatter. Now, Dirac did that in 1930 and 1931, predicted that there would be this stuff called antimatter that was discovered in the following year. And that is regarded by many theorists as perhaps the most extraordinary prediction done using pure thought, relativity, and quantum mechanics. Now, just to give a sense of how remarkable that was, if you go to any cosmology class now, they'll tell you that in the very first moments of the universe, matter and antimatter were present in quantities. So Dirac can be said to have conceived antimatter, that half the universe, in his head, not through an experiment, by combining relativity and quantum mechanics. And that, I submit, is the basis of why we believe so strongly in the gauge theories we were talking about earlier, and now a string theory today, because they are fundamentally based on special relativity and on quantum mechanics, those two foundational theories of the 20th century, theories that have never been refuted by experiment.
And speaking about experiments, we have the Large Hadron Collider, perhaps one of the most expensive pieces of machinery in physics ever built, costing over $10 billion. And it found the Higgs boson, which helps us to complete the Standard Model, a model of quarks and what have you, that people call the theory of almost everything. So we have a theory that gives us a pretty good description of matter, but people are not satisfied. Some people think that the Standard Model is perhaps one of the ugliest theories ever proposed in the history of science. And can ugliness be a criterion for physics? What are your thoughts?
Well, first of all, it isn't the most beautiful theory. This is a Standard Model of the forces that govern what's going on inside atoms. That is true. But it's also true that that theory has never been found wanting. It describes everything going on inside atoms, and indeed it led to the prediction of its last piece, the Higgs boson, which was triumphantly discovered in 2012. But there's a real problem there. The Standard Model does not include an account of gravity. And physicists like Einstein and the great people, his peers, they always want to generalize. They want to extend theories more and more. So what theorists want is they want a theory that brings together not just the forces operating within the atom, but also gravity.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're talking about the search for a theory of everything, using pure mathematics to reveal the deepest secrets of Mother Nature. Is it all an illusion? Is it a wild goose chase? Or are we on to something, perhaps the culmination of 2,000 years of investigation into the nature of matter begun by the Greeks 2 millennia ago? With us today is Dr. Graham Farmiloe. The book is called The Universe Speaks in Numbers. Well, we began with Newton's theory of gravity, which can be reduced to calculus and mathematics. Then we have Maxwell's equations, which show us how something called tensor calculus can give us electricity and magnetism. And then when you apply tensor calculus to curved manifolds, bingo, out comes Einstein's theory of gravity. And then we have this bizarre theory called the quantum theory, which describes the nuclear force and the atomic forces inside the atom. And now some people think that the greatest chase in all of physics is to marry these two great theories. On one hand, we have the theory of the very big, given by Einstein. And then on the other hand, we have the theory of the very small, given by quantum mechanics. Some people think that there's a new theory called string theory, which is our best bet. So explain to us, what is string theory?
Well, the first thing to say, the most important thing to say about string theory is that when it first shot to the headlines in 1984, it was really a generalization. It was a bigger form of the Standard Model that we've been talking about, the model of atomic forces, that also demonstrated why gravity had to exist. Now, my colleague here at the Institute for Advanced Study in Princeton, Edward Witten, who's perhaps the greatest theoretical physicist of the last 50 years, was saying that fact, that this structure, known as string theory, actually tells you that gravity must exist was the primary reason for studying it. And it's also important to remember it's not just pulled out of nowhere. That string theory is based fundamentally on quantum mechanics and relativity. That is absolutely crucial. So it's grounded in theories that are extremely well established and have never been refuted. Now, according to string theory, its earliest guide, if you can call it that, it says that these particles, like the electron, the quark, the muon, and what have you, they are all excitations of one simple thing, a string. You can regard them like harmonies or of a single piece of string. Now, the math of that is really very challenging, but nonetheless, the theory could be developed by physicists and mathematicians working in equal harness. The challenge is that theory sits most comfortably at extremely high energies, so it's very difficult it was very difficult for that theory to make predictions that could be tested in the lab, and that's why there was this backlash against, or one of the reasons why there was this backlash against string theory, because it wasn't making predictions that could be tested in the lab, and the string theorists were accused increasingly of doing cerebral things in their brain that were not related to the real world.
Okay, well, if you take a look at the history of science, with Isaac Newton's theory of gravity, we could calculate the motion of comets,
Yep.
the motion of planets.
Mm-hmm.
With Maxwell's theory of light, we could actually calculate the speed of light from first principles. With Einstein's theory of general relativity, well, we have black holes and gravity waves and the perihelion of Mercury, ... The list goes on and on and on.
Mm-hmm.
Quantum mechanics, we have the fact we have modern electronics, transistors, lasers, all of which are a byproduct of quantum mechanics. But string theory talks about universes. To test string theory requires you to create a baby universe, to become God, to create a baby universe in a laboratory. And some people think, well, that's patently nonsense. Who can even conceive of creating a baby universe in your laboratory and become God yourself? How do you defend yourself?
Well, the first thing to say is I agree with, I think it's Daniel Amati who said that string theory is a theory from the 21st century that fell by accident in the 20th century. There is no completely clear understanding of string theory. That's a very important thing to say. In my book, The Universe Speaks in Numbers, I think I always call it the string framework, and it's a framework that we're still trying to understand. So in my view, it's premature to expect that framework to be making concrete predictions, but the stakes are incredibly high. We're talking about trying to find a theory that goes beyond our atomic forces and gravity and pulls them all together, and it can be shown quite straightforwardly that such a theory like that is always going to be extremely difficult to test, and it's going to be testable only at the very highest energies, and that unfortunately has made it very, very difficult to test. But the mathematics of that theory has proved rich. It has been a boon to mathematicians, and mathematicians have done great work in elucidating string theory. So I believe we're in a position whereby the theory is that it has so much mathematical beauty to it that it seems to most experts that I've spoken to, people that really know what they're talking about, the frontiers of this subject, particularly along this corridor at the Institute, that there is so much going on for that theory that it seems very likely that there is something right in it. And we've yet to understand the theory in full, but it is extremely promising, and it is the only generalization of those gauge theories that is interesting.
We have to, unfortunately, wind up the hour. Once again, this is Science Fantastic with Professor Michio Kaku. Our special guest today was Dr. Graham Farmiloe. The book is called The Universe Speaks in Numbers, How Modern Math Reveals Nature's Deepest Secrets. And like I said, I have my own prejudices about this. I work in string theory. However, I also know the critics of string theory, and you have to have a balanced point of view.